Well, welcome for this afternoon's seminar. We're about to begin. But before we do, we're supposed to be aware that we know where the exit signs are in case we need to leave the room on a short basis. And with that, those that are on the internet, we strongly encourage you for the Q&A to send your emails to the address that's shown below on your monitor. And this way we can pretty much guarantee that we'll take your questions on time. So with that, Matthias.
Thank you. I want to welcome the people in the room and on the internet. I'm pleased to welcome Dr. Mark Fisher here today to give his presentation. We're here today because California has committed to ambitious plans to reduce statewide greenhouse gas emissions to 1990 levels by 2020 under AB 32, and we have further reductions planned under SB 32. Methane, for example, is an important short-lived climate pollutant, and we need the reductions to meet short-term targets while we get our arms around CO2. SB 1383, for example, requires us to meet a 40% reduction in methane emissions from 2013 levels by 2030. Regulating and inventorying of methane is a relatively new process for this agency, and Mark's work is an important component of our broader methane research program that will inform our inventories and allow us to develop policy and regulations to achieve these reduction targets in California. Dr. Mark Fisher is a staff scientist in the Sustainable Energy Systems Group and Energy Technology area at the Lawrence Berkeley National Laboratory. He also holds an appointment as an associate researcher at the Air Quality Research Center at the University of California in Davis. He received his BS, MS, and PhD degrees in physics from MIT, University of Illinois, and the University of California in Berkeley, respectively. His work focuses on quantifying and mitigating Earth-radiated forcing due to greenhouse gases and human habitation. Furthermore, he is interested in the development of sustainable solutions for energy-related environmental problems. His work specifically focuses on the development and application of measurement technologies for atmospheric trace gases, the modeling of atmospheric greenhouse gas concentrations, and solar radiative forcing in response to air pollution, quantification of greenhouse gas emissions from facility regional scales, and the identification of cost-effective options to mitigate emissions and reduce radiative forcing in the climate system. So without much further ado, I want to welcome Dr. Mark Fisher and hand the microphone over to him.
Matthias, thank you very much for the kind introduction. Thank you all for coming. I'm going to tell you about a project that we've conducted for the Air Resources Board for sort of the last 3-4 years. This is a combination of atmospheric measurements and inverse modeling to improve estimates of greenhouse gas emissions. Let me start by thanking a broad cast of characters who have made this work possible. In 15 years ago, Guido Franco at the Energy Commission invited me to come and talk about the possibility of making atmospheric measurements, and Guido pushed forward our research, and I owe him a debt of gratitude. Following the work for the Energy Commission, Bart Croes, Mike Fitzgibbon, Jorn Horner encouraged us to continue work for the Air Resources Board, and the group has now grown to include a host of additional individuals at ARB who are making the work that we have conducted really just a starting point. I also want to thank Ying-Kang Su, in particular because of his early support for our work, Matthias, Falk, Abalash, Vian, for their more recent advice and assistance. The work that we're going to describe today was conducted primarily by Senglin Zhang in our Sustainable Energy System Group, and terms of the modeling, Seng-On has really taken a lead role. Xinhuang Cui and Justin Bagley also contributed very substantially. At Caltech, we could not have done this work without Sally Newman, and at UC Riverside, Jingsong Zhang provided essential support for the station in San Bernardino that I'll describe. Beyond that immediate group, I want to thank the National Oceanographic and Atmospheric Administration, in particular Arlen Andrews and the whole Tall Tower group at NOAA. The work that we're doing is vitally influenced and contributed to by their effort. Beyond those folks, there is a long list of people who I'm not going to name individually, but I'm just going to say are critical parts of what is now the California Greenhouse Gas Measurement Network. Finally, this work was supported by the Air Resources Board under Project 11306. To give you an outline for the talk, I'll start by very briefly outlining California greenhouse gas emissions. I think everyone is probably very familiar with this, so it's going to be very brief. I'll tell you a little bit about our approach for regional inverse modeling, including sort of the measurement network and the approach for inferring emissions based on enhancements of greenhouse gas in the atmosphere, and then tell you about the results both in terms of the measurements, the numerical transport evaluation that we did to sort of figure out how good is our model, and then report on estimates of methane, nitrous oxide, and fossil fuel CO2 emissions. I'll finish with a summary and some recommendations for further work. California greenhouse gas emissions in context, I would just say I'm enormously proud to be part of probably the most serious effort globally to understand and control greenhouse gas emissions with legislated requirements. You're all probably more familiar with the details of those, at least the folks in the immediate audience. But the idea of reducing emissions by 80% by 2050 seems like it would be such a tremendous success to be able to achieve that, that it just feels very positive and fortunate to be part of a political entity that's at least going to try to do that. Now, the hard part. The plot on the upper right shows ARB estimates of emissions over time. The long blue bars are, light blue bars are CO2, and that's primarily from fossil fuel combustion, and that is going to be a huge part of the needed reduction and an enormous challenge in terms of transforming our energy system. In addition to CO2, the little red, even smaller green, and then little purple bars indicate emissions of methane, nitrous oxide, and essentially industrial pollutants, high global warming potential gases that are used for refrigerants predominantly. And what the main substance of this talk will be on are those methane and nitrous oxide emissions. We'll touch on the fossil fuel CO2 portion, but as I will show you, data is at this point still lacking to really nail down the fossil fuel CO2, and I'll explain why that is. So in terms of where the emissions are coming from, the lower circle shows that roughly 40% is coming from transportation, and that is going to be the enormous challenge for our car-centric land, and that we have people tuning in remotely seems like a positive step in that sense. Now, I'm going to jump into how we make regional estimates of greenhouse gas emissions, and I hope that everyone can see this little cursor. I can see it. Is everybody else able to see it? What we do here, in the simplest possible sense, is to measure how much greenhouse gas is in the air above California, and first try to estimate what part of that air, what part of that greenhouse gas in the air above California came from California as opposed to coming from outside California. And then of that part that came from within California, estimate the coupling back to the surface, indicating where it came from and just how much had to be emitted to give us those enhancements in the atmosphere. And the reason this is complicated is that the atmosphere is a constantly moving, constantly diluting test tube in some sense. And so what we're going to try to do is use a model for how emissions from the surface enter the atmosphere to produce a concentration difference, and from that work backwards to what the emissions must have been to give us the measurements we see. So it's called an inverse model because we're trying to infer emissions based on concentration enhancements. The way we do this is, first of all, make lots of measurements above California. And in this project, we've used towers. The upper left plot, which I'm sort of trying to scroll around on, shows yellow dots where we have sites where we make measurements. And those measurements happen every hour of every day for years at a time, and then that gives us a big data set that we have to work with. Now, that's what's in California, but as I'll show you in a minute, it's not only from California, it's also from outside California. And so the plot in the middle upper is a plot of methane as a function of latitude and year, showing that globally, methane has a measurable concentration in the atmosphere, and if we go to sites that are remote from essentially human influence, we can get sort of an average mixture of methane, and from that infer something about the methane that's entering the air above California from outside. So that's what we call background inflow. Now, those two things taken together with their uncertainties will give us a sense of how much methane is being added to, or not how much methane is being added to the atmosphere, but the concentration enhancement of methane in the atmosphere above California. Now, to estimate how much emission we need in order to give us that enhancement, we start with a prior emission model in the upper right, and we combine that with an atmospheric transport model that you see whirling around here to produce what we call a predicted methane signal. Once we have the predicted signal and the measured signal, we can compare them in what we've called here a statistical estimator of emissions. And from that get an improved estimate of what the emissions in the upper right had to be in order to give us something where the measurements and the predictions match. Okay, now I'm going to change course a little bit and say something about the measurements. In order to be able to say how much gas is there in the atmosphere above California that actually is coming from California, we not only have to make a measurement of the air there, but we have to be able to put it on the same measurement scale, that is, accurately know its concentration as compared with that background air concentration, which is being made by a different set of instruments in a different place at a different time. And combining that together requires having what is essentially called a network standard for the measurements that you're making. And for some gases, that's much harder than others. And I'll tell you a little bit about methane and nitrous oxide here because they're the focus of this talk. What we do is find tall towers in California. Two that we have been using for this work are at Walnut Grove, which is just 30 miles south of Sacramento or so, and then the San Bernardino Tower, which is down here in Southern California. In addition to those two towers, there are a host of other towers operated by different groups across the state who collaborated on this work to be able to produce a California-wide estimate. Every tower has to be accurate, precise, and on the same measurement scale. In other words, when one says it's 400 parts per million CO2 and the other one says it's 410, you have to be sure that that difference really is 10. And so what we do is we run a series of very high quality instruments. This plot here shows racks full of measurement instrumentation, and it critically, in the background, calibration gases, which are produced by NOAA and produce a uniform standard that we can then take to each of the sites and make sure that the instruments are measuring the same thing when you put the same known quantity into them. In addition to those calibrated continuous measurements, we also do flask sampling that provides an added check on the measurements and additional tracers to tell us something about the sources of the emission that, for methane or nitrous oxide or fossil fuel that we're measuring. In particular, and I'll just mention it once here and then come back to it later, radiocarbon 14CO2 is sort of a critical measure for fossil fuel CO2 combustion because fossil fuels are millions of years old and contain no more radiocarbon. All the radiocarbon is decayed away. And so when you see a depletion of radiocarbon in the atmosphere, you can reasonably reliably understand that as CO2 being emitted from fossil fuels and depleting the radiocarbon relative to the non-radiocarbon. So I won't go into that more now, but we'll come back to it. So here we go, estimating local signals. Global greenhouse gas background inflow, in general, will dominate the local measurement of total greenhouse gas concentration. These plots show methane and nitrous oxide measured at Walnut Grove at 91 meters over many years, and what you see are black dots representing the local measurement in the top of each of these panels with a little red line under it indicating the background concentration. If we blow that up so that the bottom of the scale is no longer zero concentration but is sort of the minimum observed, you can see that the background enhancements are often only a small part of that background, and so measuring the background accurately is critical. That bottom plots here show the local minus background enhancements. That's what we're after. Okay? Now, we do that not for one site or two sites, but now California is almost unparalleled in terms of the number of sites for a single geopolitical entity of a finite small size that has numerous measurements. And for methane, for example, there are now 13 stations operating, measuring methane continuously. The Air Resources Board operates 6 of those. In addition, there are roughly 6 sites, maybe perhaps more now, measuring nitrous oxide. And during this study, we had 3 sites that were measuring fossil fuel CO2 through that radiocarbon method. So that's, for fossil fuel CO2, kind of limited. Now, I'm going to turn back to this problem of inferring emissions. And I want to just preface this slide by saying this is a description of a Bayesian estimator method, which in the simplest possible terms can be boiled down to the following. When you want to estimate something that you can also measure, you can compare your measured signal with your predicted signal for many, many examples and make what essentially becomes a scatter plot. If, in general, your measurements are higher in local concentration than your predicted signal, it suggests that there needs to be more emission in order to give you the concentration that you predict. I mean, to give the concentration that you measure. Sorry. Now, in practice, you have uncertainty in measurements, you have uncertainty in your transport model, and you have, critically, uncertainty in your prior model for emissions. And the reason that that's important is that we actually know the emissions of these greenhouse gases better than zero. In other words, we have some understanding of where they're coming from, and we have some, many of you in the audience have spent parts of your careers developing inventories for these gases. There is a great deal of knowledge. And so what we were trying to do in this approach is to incorporate each of those bodies of knowledge in a way that weights their uncertainties appropriately. And that's not an easy problem. We've taken a particular approach here, which we call a hierarchical Bayesian method, to do that. But in another sense, you can drop back mentally and just think, this is a comparison of predictions versus measurements. And if the measurements are much bigger than the predictions, we've got to have more emissions to explain it. On the other hand, if the predictions are much bigger, it's likely the emissions are actually lower than the prior model. So here we've estimated scaling factors for emissions on 0.3 degree pixels covering the state. So what that means is we take our model for the emissions in each of those pixels, and then we run it through a transport model to produce predicted signals. And we do that in a Monte Carlo simulation many, many times, altering the amount of emission from that pixel by some multiplicative factor to generate better estimates of what those emissions are. In addition to that, we estimate uncertainties in transport, we estimate the uncertainty in the prior model, and we compare that with estimates of those quantities from other sources. So you can read about this. A paper has just been accepted in the Journal of Geophysical Research, Atmospheres, by Seung-Eun Jong, and I'm happy to share that with you after the talk. Here's an example of this hierarchical Bayesian method applied to estimating both the uncertainties in different quantities that go into this model. And so on the lower left, there's a histogram that shows the probability distribution for the uncertainty in emissions. And what this shows is that the median emissions, median equals 1.47, is about 50% higher than the a priori estimate, and the confidence interval ranges from sort of 0.9 to 2.2. Similarly, there is on the right an estimate of the standard error in the model measurement uncertainty. And what that means is, how well do we know for a given measurement and prediction how well they ought to match? How much will the transport-related uncertainties cause that difference to dither around? So that's another part of this inverse estimate. Now, I'm going to step back another bit and talk about atmospheric transport. We would not trust the inverse model estimates of emission without testing whether our transport model is capable of both producing the measured variables like wind velocity and planetary boundary layer depth that go into producing the predicted signals without testing it. And so we spent the fair fraction of a year actually in doing the analysis and many years in developing the method to compare our predicted winds and boundary layers with our predictions. And this figure shows in the upper left, three plots of California, one with the stations that we used for essentially surface observations, on the left in A, in the middle in B, the wind profiler and LIDAR sites that we used, and in C, right here, if you can see, the sites where we had carbon monoxide measurements, which we then used to compare with predicted carbon monoxide, where under the assumption that we have some knowledge of the carbon monoxide emissions. And that, we believe, we have some handle on because the Air Resources Board has spent more than a decade, many decades, controlling carbon monoxide and understanding its emissions. So it's believed to be a reasonably well-known tracer, at least at regional to statewide scales. Now, when we do these simulations, we run what's called a weather research forecast model developed at NCAR and substantially enhanced with a stochastic, time-inverted Lagrangian transport model called STILT, which was developed at Harvard University and then further implemented on a large scale by atmospheric and environmental research, also in Massachusetts. They've been kind enough to share all of this code openly. You're all welcome to try to use it. And we have essentially tried to build on that to make it useful for California. The bottom figure here shows what we call the domains of our modeling, an outer grid covering sort of most of the western US at 12 kilometers, nesting down in subsequently smaller grids to 1.3 kilometers, actually 4 kilometers for all of California and 1.3 kilometers for the Bay Area and the South Coast Air Basin. Okay, in terms of comparing the key variables from this weather research forecast model, we start by taking measurements at wind profiler stations where we know the wind velocity is a function of altitude above the site, and then comparing it with the output of the WRF model. And we also take boundary layer depths either from the wind profilers or from LIDARs and compare those with boundary layer depths predicted by the model. Those are both critical variables for estimating essentially that coupling between land surface emissions and enhancements in the atmosphere. When we do this, we find that the agreements are not always what we'd like them to be, and we adjust the schemes for describing essentially the atmospheric physics in WRF to find essentially a modeling scheme which gives us the best representation relative to the measurements for these multiple sites across California. And as an example, or a couple of examples, the upper plot on the right here shows at the Irvine profiler and at the San Jose State LIDAR predicted and observed boundary layer depths for sort of midday periods. And what you see is that after optimizing the model using a subset of stations, the remaining stations that we use essentially as a test have a reasonably good correspondence between observation and simulation, but with a fair amount of noise in it. That is, in an individual hour, there's a scatter, but there is not a statistically significant bias. And that is important because if we have a bias, it would translate all the way through the modeling system to a bias in our emission estimates. We do the same thing for winds. These lower plots here show predicted and measured winds. And the bottom line of all of this is that after working on this for, well, it's now been a decade almost, if we essentially pick the best representation of physics in WRF, we can generally get the wind speeds within about a half a meter a second, the wind directions on order 15 degrees, and the boundary layer depths to within a couple hundred meters, which is about as good as at least as the wind profilers would do. The LIDARs can probably measure a little better than that. So with that done, we then compare, well, here are footprints. I'm not going to spend much time on this. I'm just going to say a footprint is an essential intermediate step to estimating those concentration enhancements in the atmosphere based on land surface emissions. In some sense, what these maps show you is that for every site where we're measuring, there is a sensitivity to surface emissions of greenhouse gas that has units here of ppb per nanomole per meter squared per second. The way of thinking about this is for every nanomole per meter squared per second of emission from a given patch of land surface, we're going to get a certain number of ppb at a given tower in terms of an enhancement in concentration. These are essentially the sum total information that we get from that Whorf-Stilt model in terms of predicting concentration. We multiply these maps by the surface emission in the prior model to get signals. I'm not going to take questions right now, but we can come back to this later. We do this for every hour of every day for all the different sites, and then we have a way of calculating predicted signals. And as a start, we did that for carbon monoxide for 6 different sites across California. And what we found was that there was scatter between, let me just point to you for one. This is Caltech. The time series are shown here where there's observed and predicted signals as time series and then as scatter plots on the right. And what you see is that in general, there's scatter about the one-to-one line, the unity line, but there are not significant biases. There are a few sites, I will qualify, where there were more significant biases, and those were places generally where we had stagnant air building up, for example, at the end of the southern San Joaquin Valley, where the mountains sort of create a bowl where the air can't easily transport, and it's very difficult to predict the air motions. With that exception, we generally are able to predict CO pretty well across the state. And on the basis of this, here's another plot for winter and spring instead of the other seasons. We're able to estimate that on a statewide basis, we believe that we can estimate greenhouse gas emissions with an sort of uncertainty in that overall bias of about 10%. And there are plenty of caveats to that statement. For example, do we really know the detailed distribution of the CO emissions everywhere and all the time? Probably not. We worked pretty hard here to blank out periods where there were fires. You can see in this plot here, there are these red flag dots here when we knew there were fires nearby a given site, and we didn't include those in the prediction measurement comparison. But you know, it is possible that we're missing something in the details of the emissions. We believe that at this point we're doing a reasonably good job. I'll show you in a minute that for greenhouse gases, the differences between our a priori knowledge of emissions and our essentially posterior knowledge based on the atmospheric measurements, that the differences are larger than 10%. And I would say in cases where that difference starts to get down to the level of about 10%, I would at this point have a hard time telling you, yeah, we're sure that there's emission differences. I mean, I just don't think we can do it that well yet. But at the level of 30 to 50%, I think we can. And so let me jump into methane. Methane is the gas that we started on earliest. At Walnut Grove, we started measuring in October of 2007 and have had a long history of trying to understand methane emissions. Now we're at the point of having 13 different stations across California that we're measuring methane during this sort of project measurement period, which ran from June of 2013 through May of 2014. And what we found from this was that in general, we were able to predict the sort of lower limit of our measurements from the background reasonably well. These plots each have, for a different site, a time series with blue dots showing background, then green triangles showing prediction of local signal plus background, and then red being the actual measurements at the given site. And in general, we found the background signals look reasonable, but also the prediction plus background for many of the sites was not as strong as the measurement. In other words, we're measuring more methane than would be predicted by the combination of the background and the transport model with the prior emissions, suggesting that there's probably more emission of methane than in the prior model. So now I'm going to say a little bit about the prior model. The prior model for methane is something that I take real pride in. My group's been working on it since 2005, and we have been trying to assemble the best possible geospatially and temporally specific information on methane emissions from California as we can. That said, we've produced a map that has 10 by 10 kilometer spatial resolution, but I don't believe that we necessarily know the overall emission factors for all of those different sources of methane. For example, how many kilograms of methane are coming from each cow? The Air Resources Board has done a tremendous amount of work developing that kind of inventory-based emission factor information and overall counts of cows at the statewide basis. And we have adopted the Air Resources Board estimates of those prior emissions as an overall scaling on each of our subsectors. And so while this has got spatial resolution, which is not typically part of the official inventory, it has been scaled to the overall inventory for the year 2012 based on the version of the ARB inventory from 2014. And we've done that by source sector with some additional adjustments for regions. We've also included seasonal emissions, seasonally varying emissions from both wetlands and rice agriculture because they have a strong seasonality. Arguably, some of the other sources might also have seasonality, but we believe we can pull that out of the inverse model estimates. And I guess what you should take away from this is, for California, the majority of the estimated emissions are coming from animal agriculture, followed by landfills, followed by smaller sources, including oil and gas, and so on. If you spatially disaggregate that into different regions, what you find is that in the middle plot here, the northern San Joaquin Valley has some non-trivial emissions. The San Francisco Bay Area has non-trivial emissions. The southern San Joaquin Valley has very large emissions because that's where most of the animals are in California. And then South Coast Air Basin also has non-trivial emissions. And that's not animals so much, that's much more landfills and human activity like natural gas, leakage, we believe. I'm waving my hands there because we're not sure about that. And then finally, I'm just going to show you this plot on the far right are the California air basins that we then will sum our emissions model output into to give you sort of regionally specific estimates of emissions. Okay? Now, this plot shows predicted and measured methane from all the sites involved in the study over time, both for, in each case, the prior model and the posterior model. So the prior model is what we start with based on our emission inventory, and the posterior model is after combining the measurements with the prior model to say, how should we adjust the prior model? And the thing to take away from this is that, well, for some of these periods, the predicted measurements agree with the predicted signals, agree with the measurements reasonably well. For example, this very uppermost left plot, and the posterior doesn't differ substantially. But for some of these others, For example, the upper right, the prior model is significantly lower in prediction than the measurements. In other words, that solid line there is not along the diagonal of the plot, indicating that measurements are stronger than predictions, and therefore emissions are likely stronger than the prior model for emissions. However, the posterior model agrees much better between the prediction and the measurement, indicating that what we've effectively done is to adjust emissions upward to create a better match within the limits of our sort of collective uncertainty. We do this for 3-month periods at a time, and so for a year there's 4 different sets of plots on here, and we do that in a Monte Carlo simulation because we're estimating multiple parameters that are non-linearly related to each other, so we can't use a simple matrix inversion. And we then have, in sum, a posterior estimate for emissions for methane from the different regions of the state, initially with the 0.3 degree resolution, which we can then sum into either entire state and entire year, which is where I'm going to start, or sub-regions and sub-time periods. Here, this plot shows methane emissions by season and sector across all of California summed together. So this is the state total. And what we find are that the emissions are roughly 2.4 plus or minus 0.5 teragrams of methane at 95% confidence, equivalent to 1.2 to 1.8 times the ARB inventory of 1.6 teragrams methane that we used as our prior model. If we allow for the fact that there might be a 10% bias in our transport, that knocks things down a little bit so that we're sort of between 1 and 1.6 times larger than the current inventory. But, you know, in sum, it looks as though there's a pretty compelling body of evidence for more emissions than in the current inventory, but not by an enormous amount, not by a factor of 2, by sort of, 30% in the median. Now, one of the things you can look at here in the lower plot is the emissions by season. And if you sum across the state, you find that the posterior emissions, after correcting for wetlands and rice, are reasonably constant, with a little bit less in spring, arguably, but at 95% confidence, all of these emission estimates are essentially similar to each other. Now, we can also disaggregate those emissions into source sectors by just looking at how the individual pixels have contributions from individual source sectors, and then summing across the source sector scaling, the pixel scaling for all the different pixels, but weighted by the relative contribution from source sectors. And what this shows you is essentially what we started with, that dairy livestock on the far left of this figure dominates the emissions, with some emissions from non-dairy livestock, some emissions from landfills, LF, natural gas, and then several other smaller sectors. So, in summary, emissions of methane appear to be slightly higher than the current inventory, and the bulk of that difference appears to be in the dairy livestock sector. Now, we can also sum emissions just by region, and these regions are shown in the plot on the lower left. Region 3 is sort of the Sacramento Valley. Region 7 is the San Francisco Bay Area. Region 8 is the San Joaquin Valley, and Region 12 is the South Coast Air Basin. And what you see from this is that with the exception of Region 8, the San Joaquin Valley, the other emission estimates, posterior emission estimates, overlap with the prior estimates at 95% confidence, suggesting that only Region 8 is statistically different at a significant level from the prior. Now, we've also, for the South Coast Air Basin, where a lot of work has been conducted on methane, compared this work with several different previous studies on the lower right. And what you see is our prior estimate on the left, and then a series of studies starting with Wunsch, Su, Wenberg, Kui, Spatial, Wecht, Wong, and then this study. And they're effectively at 95% essentially consistent with each other and with an emission from the South Coast that's on order 350 to 400 gigagrams. So that's not the majority of California emissions. It's just the place where we found the most studies to compare with. Okay, now let me take a step back on methane and give you a sense of what the spatial distribution looks like in the posterior. And really what I'm getting at here is, does the posterior spatial distribution look like the prior spatial distribution, or are there some differences that are significant? What do they tell us? And so first, on the upper left, here is a plot of the posterior methane emissions, which at the pixel scale shows essentially that big glob of livestock in the Central Valley, some emissions from the urban areas, etc. Notice this is a logarithmic scale, so these steps are not, these are factors of each other, not just linear. If you ratio the posterior emissions to the prior emissions, this plot here shows there are a few spots where the emissions are quite a bit multiplicatively higher than the prior. If we instead plot it as a difference in gigagrams, this plot on the far right here shows a few hot spots. There's one right there in the San Joaquin Valley, and a few others that are high. There are some that are low, and one thing I want to draw attention to is often when there are hot spots in these 0.3 degree emission maps, there is a cold spot right near it. In other words, an anti-correlated pixel. And we believe that this is essentially a statistical artifact in the inversion process, so that I don't personally believe that we can identify with extremely high confidence hotspots. When we see these anti-correlations near them, we have to draw a breath of caution. If you plot the 95% upper and lower limits, you see sort of similar patterns. This one spot right here, which shows up bright here, even in the lower estimate seems to light up. So if I were to go and look for a spot with extra emissions, I might try there, but I wouldn't be surprised if it wasn't. So now, let me turn to nitrous oxide. We've looked at methane. We're going to look at nitrous oxide and then fossil fuel CO2. Nitrous oxide is even harder to measure than methane, and the reason for that is that CO2 is 400 parts per million. Methane is 2 parts per million. Nitrous oxide is a third of a part per million. So it's down more than 100 times relative to CO2, and there's lots of it floating around the Earth in a sort of uniform bath. In other words, the background is an enormous part of nitrous oxide total concentration in the atmosphere. And so getting the difference between what you're measuring and the background inflow right is a big part of getting this problem right. In addition, there are other sources of nitrous oxide besides human activity. In particular, there are likely to be emissions from ocean upwelling of nitrogen-rich species and biological activity. There's also forest soil in California, which is part of a natural nitrogen cycle that will emit some amount of nitrous oxide. And so accounting for those additional sources is important when you're trying to estimate the anthropogenic component. And for this project, Seng-Un Zhang estimated the ratio of forest and ocean N2O to the total signal that we were seeing in ocean minus prior being anthropogenic, plus ocean, in other words, total, and also forest. And what you see here is that for a couple of the sites where we measured nitrous oxide, Sutro Tower and Walnut, well, really Sutro Tower, there was a non-trivial component of the signal that was from ocean. And you'll see in a minute why that is. Sutro Tower is above San Francisco, and the air at Sutro is very heavily influenced by ocean inflow. That's sort of a background for why this problem was difficult, but we went after it in the following way. We started with a globally produced estimate of N2O emissions called the EDGAR emission data set. And we scaled it again to the ARB inventory for the anthropogenic sectors. And it doesn't say this here, but we also included another set of models for the biological sources, the Gaia model for ocean, and I can't remember which model we used for forest right now. It may have also been Gaia. And then we produced essentially maps of anthropogenic emissions on the left, roughly 50 gigograms of N2O a year, forest, roughly 2, and then ocean doesn't really have a sum in terms of emissions because it's offshore, but we can then calculate from that emission map how much of a signal we're going to get onshore as essentially a perturbation to the background. And what we find is that most of the emissions are coming, again, from the Central Valley, and then maybe a third from the urban regions. And the largest emissions are agricultural soils, and that's because we're pouring nitrogen fertilizer into our agricultural systems to make lots of vegetables and other things. And some part of that nitrogen application ends up in the air as nitrous oxide. In addition, there are industrial processes and product use. Every time you have whipped cream with your dinner, you should whip it by hand, and manure management. Okay, so going back to the plots comparing measurements and predictions, here we have, in almost every case, predicted versus measured N2O across the sites we measured lower than the measurement. In other words, predicted N2O is uniformly under-predicting what we actually observe, suggesting that uniformly there is more emission than the prior model. And we've done this, again in this hierarchical Bayesian method, many simulations to try to estimate the noise in this estimation process. And in summary, the state anthropogenic N2O emissions are roughly 1.5 to 2.5 times the ARB inventory for 2012. And if we scale that downward, accepting the possibility of this 10% transport bias, maybe 1.3 to 2.3 times. So here, even more substantial difference from prior than for methane. And I'm personally not enormously surprised by that, because if the predominant source of N2O are things like nitrogen processing of agriculturally applied fertilizer or processing of manure waste. I could imagine there being enough different subtleties to the biogeochemical process that one's prior model wouldn't necessarily capture that. Now, I think ARB is putting a lot of work, very useful and important work, into understanding these agricultural emissions better, and I have a feeling that this will be resolved in the not too distant future. It is also possible that there is some other source of nitrous oxide that we just didn't include in the inventory, but I find that a little less likely. Now, I guess I would summarize here by saying emissions are likely higher than we have in the prior model. They, for better or for worse, don't appear to have a strong seasonal variation, and that is not enormously surprising because California's climate is relatively moderate compared to the continental interior, where previous measurements had shown much more dynamic variation between winter and summer. I guess I will turn now to emissions by sector. Because we don't have really good tracers yet for different sources of nitrous oxide, we've made some progress on that, but not for this large number of sites. The thing that we can do reasonably well with this model and measurement combination is to say something about the regional estimates of emissions as opposed to the source sector. I'm a little more cautious about source sector, but based on the regions, here, Region 8, the San Joaquin Valley, is again the place where we're seeing the largest posterior prior difference. And so it appears that it is that the Central Valley agriculture, which is the source of this underestimate of nitrous oxide in the largest sense. If we zoom in on what the maps of nitrous oxide emissions look like, in the posterior, the Central Valley is where most of the action is, with some in the South Coast and some in the Bay Area, but small by comparison. But what's interesting is that the posterior difference, which is the only plot here that I'm going to focus on right now, shows sort of a band of enhancement that is posterior greater than prior all through the Central Valley, with several spots that are showing up particularly strongly. But remember, now this is a linear plot, so if those spots had high emissions, on a log scale in the prior, if they get a little bit stronger in a fractional sense, they show up very strongly on a linear difference plot. So that's a caveat there. Okay. Now I'm going to turn to fossil fuel CO2. And here we, again, are comparing measurements with predictions. The predictions are produced using a prior model for fossil fuel CO2 emissions that were produced by Kevin Gurney's group at Arizona State. It's called the Vulcan 2.2, that's the version, fossil fuel CO2 emission model. We scaled Vulcan to the ARB inventory by source sector for 2012. And you can see in this plot that for the different source sectors, there are, in some cases, differences between the initial Vulcan and the scaled Vulcan, but they're, with the exception perhaps of power production, fractionally not enormous. Now, going back to why we measure radiocarbon. Radiocarbon, as I said before, provides a sensitive measure of fossil fuel additions of CO2 to the atmosphere. And I didn't say this before, but I'm going to say it now. The reason that matters is that if you just measured total CO2, you'd also be influenced by the breathing of the biosphere. In other words, plants are taking CO2 out of the atmosphere to grow, and soils and microbes are releasing CO2 back to the atmosphere in a terrestrial carbon cycle that is very, very powerful relative to fossil fuel CO2 emissions, except for the dense urban regions where we've got lots of motor vehicles and other activities operating. So for vast stretches of California, most of what you're going to see is the terrestrial biosphere, not the fossil fuels. And in order to be able to say across California, what are fossil fuels doing, we need something that is really specific to them, and that's what this radiocarbon gives us. Okay? So using the Vulcan model and measurements of radiocarbon, where those are a very difficult measurement, you have to essentially take a sample of CO2, reduce it to graphite by removing all the oxygen, take that little lump of graphite and stick it in an accelerator. There's one at Livermore Lab, there's one at UC Irvine. They're few and far between, and at $300 a pop, you get a single measurement of how much C14 there is, and therefore how much radiocarbon fossil fuel CO2. And you can imagine that that will eat into your research budget pretty quickly if you start trying to do thousands of samples, not to mention the effort required to do all the work of reducing and then measuring. So fortunately, the National Oceanographic and Atmospheric Administration has made the Walnut Grove Tower a place where they've been measuring radiocarbon CO2 for almost 4 or 5 years now, since 2009. So actually now it's 6 years. And we used that in this model, in this study, to look at Central California, because that's where the Walnut Grove Tower is sensitive to, and estimate, that's, in a very coarse way, how much how much fossil fuel CO2 is there in the atmosphere relative to our predictions, and then from that, whether the inventory for emissions is roughly right or not. And in long story short, the plot on the lower right here shows predicted fossil fuel signal versus measured fossil fuel signal, and the best fit line is essentially within 10% of the one-to-one line, indicating that there isn't any strong evidence of a significant bias in emissions. We did the same thing for a much, much smaller data set from San Bernardino and Caltech and found similar but not identical results. San Bernardino actually looked a little low, and we're still trying to figure that out. So I'm going to just summarize and list some recommendations. In summary, this work is a culmination of a decade of effort on the part of my group, and was possible because the Air Resources Board trusted us and worked with us to do this. The continued multi-species measurements at Walnut Grove and the new measurements at San Bernardino added to the ARB measurement capability, and the generous collaborative activity of many other people's groups made it possible to put together a network of sites. We've optimized the NCAR research weather research forecast model for California. There is still more work to do there, but we believe that we've got it under control well enough to get to the point of the results of this study. And for methane, nitrous oxide, and fossil fuel CO2, we find that both methane and nitrous oxide are likely underestimated in the current inventory. Fossil fuel likely consistent. And in recommendation, I would suggest that a first order priority would be to perform a first-order uncertainty analysis of prior emissions to see whether our current prior models have flaws in them, and to produce essentially a better representation of those emissions that is specific to all gases of interest for California, and then continue, and ARB is, I'm guessing, doing the former, and I know is doing the latter, expand the measurement and modeling capability. For example, I believe that ARB is implementing wind profiling measurements at greenhouse gas measurement sites. I think that is valuable. I'd like to, and I said this before the talk, emphasize that I think it would be enormously valuable to add multi-species trace gas measurements at as many sites across California as possible so that we can do source attribution in addition to this spatial disaggregation. And if I were to name a few species, I would say ethane, other light alkanes, and then some selected VOC tracers that are specific to animal agriculture and landfills. And for the latter, I would look to the work of Alan Goldstein, who has really pioneered VOC measurements for source speciation. And then finally, bring in other data sets. And I think ARB is actually right at this moment engaged in both airborne and ground-based, essentially measurements specific to individual facilities that will help identify the sources in a more quantitative fashion. Thank you. How do you want to do questions? From the audience here first and then the folks external, or yeah? Or do you want to do the external people first? All right?
2 questions.
Okay. Question number 1, Chuck Hakarian asks, balancing greenhouse gases over California requires measurements of emissions, atmospheric concentrations, transport parameters, and removal from the atmosphere by soils, vegetation, inland waters, and other surfaces. Please describe the methods being used in your study to quantify the removal of greenhouse gases from the atmosphere by these various uptake mechanisms. Chuck, thank you for asking the question. I guess my quick response is that yes, methane is oxidized by aerobic soils, and I didn't mention it in the talk specifically, but the model that we have for, as a prior model for methane emissions from agriculture includes a soil uptake term, and I would just comment that it is small, even if you integrate it regionally compared to the sources, so it's not a big deal, but we did consider it. For methane and water bodies, I am not aware of literature suggesting strong uptake of methane by water. I think CO2 is reasonably soluble in water. But that, again, seems like a low-order term. And I have to say that for nitrous oxide, I'm not aware of strong uptake terms. And so please write to me and point out what I'm missing there. But I don't see that as a big deal. I think the nitrous oxide emission terms from natural soils almost certainly dominate. And from Stephen Wofsy at Harvard, he's very correctly asks, how were the backgrounds estimated for methane, nitrous oxide, and CO? And Steve, thank you for the question. In all 3 cases, we employed the NOAA marine boundary layer measurements that Arlen Andrews has been interpolating into essentially a background curtain, and those are specific to the year in which we made the estimates, and I guess I will stop there, and we should follow up on what I may be missing about that later.
Well, I just wanted to thank you, Professor, for Dr. Fisher, for a very, very thorough presentation. But you know, this isn't the first presentation of this kind I have attended. Good grief, it's been a decade, hasn't it?
Yes.
Yeah. So there's been a question that I've been asking, and I've been asking over and over again, because Edgar, the models that we use, the models that you mentioned, these are very, very large models with land use specificity that, shall we be honest, rather
Crude.
Yeah, good.
Yeah.
Thank you. Appreciate that. So here's the thing. We live in an era in which, I mean, you know as well as I know, that vast majority of this planet is covered by an incredible array of platforms measuring ethylene dioxide, for heaven's sake, never mind measuring formaldehyde, measuring all sorts of things, and taking pictures of every piece of, you know, if you want to know if somebody in the grasslands of Mongolia had something for lunch, you can actually figure that out if the information is available by satellites. So how is it that we have not made so much progress as to have a GIS, say, map of emissions for greenhouse gases for our so well monitored state? Question for you. Is it just a question for the community?
Mm-hmm. Yeah, Ash, it's a fair question. I would say that the use of remote sensing to prescribe activity relevant to methane or nitrous oxide emissions is an area of active research for terrestrial ecosystem processes. But for a landfill or a dairy, I would argue that the information available specific to that site from the management operations and reporting are likely to be as high or of higher quality, with some notable limitations. We know that, for example, some of the dairy maps that we used are not of the current year, and dairies open and close, so dairies might move around. There might be a shift in dairies from one part of the state to the other that isn't perfectly captured. So I guess I would agree with you and suggest that there is a valuable role for a coordinated effort to take the most current available remote sensing and attempt to refine the activity that is being used to prescribe the emissions. So, you know, with caveats, I completely agree that that's a useful exercise. It's something that was outside the scope of our project. I think it would be an interesting piece of work for either ARB to undertake or to essentially contract out to research entities. Yes. Did I cover your question? Oh, for fossil fuel, remote sensing has a real role to play, and sort of a coordinated fossil fuel data assimilation system is something that several different groups have been developing for a global application, and this is really largely focused on parts of the Earth where we have much less information about activity. For example, in parts of the world where we really have no direct handle, one can look at night lights or thermal imaging. For California, I think that the Vulcan model, while being somewhat coarse at 10 kilometers for use in urban systems, and Kevin Gurney's working on a 1 kilometer model for LA and maybe other places now. I think that we have enough essentially on the ground data sources that they just need to be assimilated. So I don't see remote sensing as being so critical for fossil fuel. Okay. Other questions? Couple, please. Was it? Wait.
Question here.
Yeah. Go ahead, sir.
Oh, okay. Since California greenhouse gas emissions are about 1% of global emissions, how much is oversimplification is to say that the stuff in the air is mostly blowing in from other places? I mean, it's not 99% from outside of California, I take it.
Well, it depends on the gas, and I'm not quite sure how to answer this question. I mean, it sort of goes back to Steve's question about background. Yeah. It depends on where you measure in the state. If you're in LA, there is a very substantial, roughly 10% increase in CO2 above background, leaving terrestrial ecosystem aside. I mean, you can get a 30 ppm increase in CO2 at a surface tower. Now that's also going to be down by a factor of 10 or 100 if you go to, a remote place in the forest. So it really depends on where you're at. But I think that it's absolutely essential that there be high quality on the same scale measurements, both in the upwind on the upwind side of California, and mercifully California is on a coast, so we get a lot of our air off the ocean. But there are actually times of year when the air is coming from the interior more, and then it's more of a challenge. I didn't really talk about that very much in this talk, but there are times a year that we blank out when we really feel like we can't get a good handle on background. So, I mean, I guess I would say, I don't think that we're making a mistake because of that, but I think that it's something that one has to remain vigilant with respect to. Yes. Please.
Yeah.
Why don't you say who you guys are so that it's on the record, I think. Peter wants that or not? You want that? Do you want people to say who they are? Doesn't matter? Okay.
This is Dave Edwards at ARB. I have a couple kind of two-part question. So I guess my first is, how would you suggest that your research supports ARB's GHG inventory development? And then secondly, in order to potentially integrate your work or apply your work to complement efforts on the GHG inventory development, what are some next steps you think would be important to take?
Thanks, Peter.
Dave.
Dave, sorry. Good questions. I felt that I touched on some of those earlier. I would say most directly, I think that on the basis of this work, we feel that there is evidence that there is a statistically significant underestimate in the current inventories for methane and nitrous oxide, and that identifying either errors in our estimation or sources for underestimate in the inventory are both important activities for getting the right answer. If you were to ask me what specific activities ought to be undertaken on the inventory side, I think I already said, I think that there needs to be effort on spatial disaggregation. And so that means is essentially building a better model than Edgar for California N2O, taking the model that we've developed for methane and finding where the obvious errors in it are and improving them, including time-dependent phenomenon like Aliso Canyon. That's kind of an easy one. For 2015 and beginning of 16, nobody's going to want to try to estimate methane emissions from the LA basin without including that source. And I think that there are increasingly, and I didn't touch on this very much, are increasingly large number of complementary activities outside of the immediate ARB research sphere that should be brought into the inventory development process. For example, the California Energy Commission has sponsored a lot of work on natural gas related methane emissions. And I've participated in some of that work, and I think that there is evidence from that work that natural gas related methane emissions are also underestimated in the current inventory. And so some examples would be gas storage facilities, not just Aliso Canyon, refineries. These are small things in the overall big picture for the state of California, but when you're doing inverse modeling, you want to be able to make sure you're getting them right. And perhaps actually important at the state level for urban areas, I think that there's some evidence that natural gas related emissions from both the distribution system and post-meter leakage also is adding to the urban atmosphere methane. Going back to the big ticket item, I think we really need better measurements of livestock methane emissions, and in particular, how better biogeochemical modeling and representation of manure management and landfill, what's the word for landfill? Remediation, essentially the fraction of the landfill methane that's effectively captured and disposed of as opposed to venting to the atmosphere. I think that number is uncertain. I mean, not being an expert, I lean that way. So does that help somewhat? I mean, I'd like to talk with you more about it because the things that we've done really are just sort of trying to point to a big picture, and I am open to being shown that we made a mistake, but I'm also really keen to see what we do actually go into making the inventory better.
All right. And with this, I'd like to thank Dr. Mark Fisher for his presentation. And we want to wrap up and close the presentation, question and answer, and the webcast now. If you have any other questions.